that pipeline is in the material that I gave everybody, so it should just be mostly drag and drop. But we're going to make two more complicated structures than just a nice React structure. The first one we're going to make is a fiber composite. Please don't yell at me, anybody who's a composites person, because it's not going to look very realistic. This is mostly just to motivate how to use the tool to make something that's not grain structures. But we're gonna make fibers that are going to be elongated. They're going to be strongly aligned along a certain axis, and we'll look at that in peer review. So that's what we're going to do next. And this will teach you how to do matrix phases and precipitate phases. So in the previous example, we only did primary. Now we're going to do matrix and precipitate. So the magic filter we need to use whenever we want to start making a synthetic structure from scratch is fast generator, which now everybody is a deep expert in. So I'm not going to explain every little detail anymore. And now we know what we want to do, right? We want to make a composite structure that has a matrix phase that fills space, and we're going to put some fibers into it. So the first thing that we notice is by default, well, I've got a primary phase. That's not the phase I want. I want a matrix phase and a precipitate phase. So the first thing I'm going to do is just get rid of the primary phase. Oh, that's right. I can't get rid of it because it's the only one there. So first thing I'll do is add a matrix phase, and then we'll get rid of it. So I'm going to click the plus button. Remember this. This is how you add new phases. It's going to warn you and say you haven't generated data for the phase yet, unless you already clicked create data. Just hit OK. It's just we're trying to protect you from yourself and end up deleting data. Okay, so I should eventually get the phase properties window that allows me to add my new phase. So this is going to be a matrix phase of like a composite material. So we're not going to do any crystallography for it. We're not going to do any weather angles. So it doesn't matter what you select for the crystal structure. I'll just leave it as default. You'll notice maybe something that might annoy some people is that for some reason we start ordering in our list of crystal structures with hexagonal. I don't know why we do that. I think it's an old, like just something from the old code, and it would be a massive headache to change at this point now that the list is pretty hard coded. So too bad it starts with hexagonal. We'll leave it at that. Fraction. So we talked a little bit about how this fraction works. We're going to actually make the two-phase structure now. So we probably want to set something here that makes sense. And I'm going to set 80%, 1.8. And you see, of course, it dynamically updates. Don't worry about that. We're going to create the second phase in a second. The phase type. So like I said, we want this to be the matrix phase. It's going to be filling space. So I'll change from primary to matrix. And I need to name the phase something, or not, but it's nice to name it. I'll just name it matrix, really inspiring name. And I'll click OK. And this is the beauty of the matrix phase. It just is the same value everywhere. So there's no statistics to set. So this is really easy. If you wanted to make a matrix phase synthetic structure that was only matrix phase, it would just be the same value everywhere. Again, we can argue that's obviously not totally realistic, but that's kind of the terminology here. Now we don't need this primary phase, so now I can get rid of it. I can exit out, so I just have the matrix phase. Now you should just have one phase matrix, and that's it. No statistics to set for this. But now we want to make our fibers. So we click plus, just like we did before. It's going to complain that we haven't generated data, which I think is kind of funny because there's no data to generate for matrix phase, so that's just the default it always does. And now we want to create fibers. So the first thing to note is that the fraction, we have to set the volume fraction. We're going to set it to 0.2 because we set the previous matrix phase to 0.8, so it's going to be about 20%. So by the way, all the numbers that I'm about to set, I have figured out ahead of time are going to make a nice looking fiber composite or a reasonably looking fiber composite. But this is where things start getting kind of, there's a bit of art to figuring out the right parameters to make something. Dream3D is going to try its best to create a structure that matches the things that you set here, but it's very easy to set numbers for things, particularly for precipitate phases, that are just physically impossible to match. That's just something that over time, if you start using the tool more, you'll kind of get used to how to set these numbers in a way that actually makes a structure that is possible to make and has the kind of statistics you want. But anyway, so we're going to do 20%. We're going to make fibers, and like I explained earlier, precipitate phases are basically just separate objects that don't fill space. So that's kind of like what fibers are going to be for us. So I'm going to make a precipitate phase, and I will name the phase fibers. Now here we do have statistics we need to set because we're going to actually make some objects. So the first thing is how big we're going to make things. So I need to look at my handy reference here. Again, these are values that I figured out worked well. And I can kind of explain when it's building why I fixed these values, but they'll become more apparent once we make our box. But we're going to set a mu of 2. We're going to set a sigma of 0.001. So we're going to really tighten up the distribution. I'm going to change my bin step size. Well, it's already on 0.5. My min max cutoffs are going to be 5. So the reason that I really squeezed up the sigma is because I want my fibers to all be kind of around the same size-ish. It's going to have one bin. It doesn't really matter for this case. We're going to say that regardless of their size, which is pretty tight anyway, all the fibers are going to have basically the same shape. Now, something that I showed earlier in the first session was this idea of preset statistics. So we have fibers, which means we're going to want them to be elongated along one axis. We could go into the B over A, C over A plots and manually change the values to get the ratios to be where we want them to be. Or a little bit easier is to just go to primary precipitate, well, in this case, precipitate rules, because we have our precipitate phase. And what this is going to do is pop a dialog box that lets us just set what we want the ratios to be, and it'll create the beta distributions for C over A and B over A for us. Again, you could do this manually, but this is just maybe a little bit easier. So I set values, I think 10 to 2 to 1. Yep. So I'm going to do this, 10 to 2 to 1. So my A axis, remember A is always, as you can see here, the following must be true. A bigger or equal to B, bigger or equal to C. And I'm making them, right, I'm making it 10 to 2 to 1. I'll hit OK. I'll hit create data. And now, assuming nothing broke, when I go up here to B over A, you can see I've got a nice peak right at 0.2. Remember, B we set was 2. And C over A should be closer to 0.1, right? Because it was 10 to 1 for that one. So that did it for me. Of course, you could have gone in here and manually changed the values, the alpha and beta parameters of the beta distribution to get plots that look like this, but this is just a little bit harder. Okay, so neighbor. So if we click on neighbor, there's not going to be anything here. And the reason there's nothing here is because remember, precipitate phases are discrete objects. There is no concept of like a direct neighbor. There is the concept of a radial distribution function, which has nothing right now because we've not created one. So we're not going to actually mess with this right now because we don't really care about having a particular RDF for our fibers. But if you did, this is where you could set the RDF. So we use RDF instead of something like 2-point statistics, would be another way to do this, maybe a little bit more robust. In theory, you could work out maybe it's Python code, what the function that would translate between your 2-point statistics, if you have that, to what an RDF would be. But this is what we chose to kind of move the precipitates, quote unquote, around the box. Nothing here because we're just going to say default. It's going to have basically just a random RDF. There's not going to be any preference to the distribution of the fibers with space. Now, ODF and MDF, we're not going to put any crystallographic properties on our fibers because they're not going to be crystalline, so we're not going to deal with these. Just leave them blank. We're not going to run the match crystallography filter, so none of this will matter. But what does matter is this guy, axis ODF. So we're going to basically make a cube texture, quote unquote, for this. We're going to make it so that the long axis, which was the A axis, is along X. The middle length axis, B, is along Y, and to the short axis, which was just 1, is going to be along Z, okay, parallel to those. So anybody know what the Euler angle for that would be? Top of your head? No. Anyone? An easy one. I mean, it's nothing, right? So it's going to be 0, 0, 0. There's no rotation of the fibers relative to the axis of the box. So the Euler angle that we care about 0, 0, 0. You know, if we wanted to rotate things so that the axes were aligned differently, we change the Euler angles. If we want to be like a, you know, along the 1, 1, 1, we change it to what, 0, 45, 0 or something, whatever. So 0, 0 for my Euler angles. And I want this to be really strong. I basically want every single fiber to be perfectly aligned. I want there to be no variance. So that means I need to give it a really big weight. So if you remember in the previous session, I talked about a little bit like weight kind of affects how strongly we favor this specific component, and sigma affects how spread out it is. So I'm going to leave sigma at 1, peaked pretty close around, right around this specific texture component of 0, 0, 0. I'm going to set the weight to an arbitrarily large number, and I'll explain like what this number really physically means. I'm going to set it to 1 million. Okay, so the first thing you should note is that the pole figure updates, and now it's really tight, you know, around the cube texture. You know, I've got my peak right at X, right at Y, right at Z, so that's great. I don't have any speckling around. All my fibers are going to be aligned like I want them. Now, real quick, this weight thing. So I mentioned that when we actually have to make our orientations, we have to sample from, you do sample from a discrete distribution at some point. So we have to bin up the ODF, in this case, the axis ODF. So this weight is related to the number of bins in orientation space, which is not documented anywhere in our documentation. It's only in the code. Okay. So we have roughly, for the different crystal structures, roughly 5-degree bins, which is pretty coarse. If you remember yesterday, when Mark was presenting on dictionary indexing, he mentioned that for that, they often default to bins that are about 1.4 degrees. It's not exact, but that's about how big they are. So when you break that down in terms of the different crystal symmetries for cubic, it's something like 5,000-ish bins, and I forget what it is for the others. So it's bigger. This is orthorhombic symmetry because it's sample symmetry. And again, I forget how many bins it is. So and if I never remember, you'll probably never remember. So this weight value is related to the number of bins. If you want to make sure that this texture component, one texture component, is basically the only texture that's chosen, you need to have a weight that is at least the number of bins, because the weight is normalized by how we discretize the space. So there is none that has more than 1 million, so that's why I usually just pick 1 million. I know that's a weird way to do it. It's not very intuitive, and I'd be happy to maybe offline if anybody has deeper questions about how that really works, talk through it with you, and I can show you in code how it works. But that's kind of why I usually pick 1 million if I want to have just one texture totally saturate the entire ODF. No matter what crystal structure, 1 million is always going to do. That's why I'm picking that. Okay, we changed some stuff, so we have to click create data. And now we've got our statistics. So ideally, we'll have a bunch of nice elongated fibers perfectly aligned with the axis of the box. And now if you remember from what we did in the last session, we have to make the box that they go in. So I've got to pop open my filter, it's not filter library, filter list. So if you recall, the filter that we use to make the box is called initialized synthetic volume. I'm going to drag that guy over. And then I have to go check what I chose for these values real quick. Sorry, and then I'll explain the order. Okay, I left it by default in this section. All right. So I actually left these as the default values. So I left the spacing of 1/4. So if you remember how to kind of relate this back to the physical sizes that we set in Stats Generator. So I've got my box in physical units is 32 in each dimension because it's 128 times 1/4. And if I go back to Stats Generator and look at my size distribution, my mean feature size is 7. So, the fibers aren't going to fully span the entire box. If you wanted to have your fibers go like all the way through the box, you'd probably want to crank down the size of the box a little bit or make this a little bit bigger. Remember though, this is, it's a little unintuitive though, because this is the equivalent sphere diameter. So it's not the like length of the a-axis, for example. The a-axis is going to be longer than that probably. So this is where it gets a little unintuitive and where you kind of have to start messing around with the values a little bit, just make some structures until you get something that matches what you want. It also means that estimate number of features isn't going to work. If I click that box, it's going to say -1, at least it should, or 1. It's not going to know how many features are going to end up in the box. And the reason is because they're precipitates. It can only really do the kind of check here for primary phases, because primary phases fill the whole volume, precipitates don't. They're, in this case, it's only taking up 20% of the water. Okay, next step is we have to tell Dream3D what shapes to use for our different phases. So that was, if you recall, establish phase or shape types. Now, unlike in the first example we did, we've got two phases now. We have a matrix and we have our fibers. Now, the matrix, you can set whatever shape type you want. It's not going to matter because it's just going to put the same. It's just going to put a value of 1 everywhere, basically. So you just leave that as default. We do want to set a shape type for the fibers. And they're going to be fibers, so it kind of makes sense for them to be cylinders. I'm going to select cylinder A. So this is going to put the flat end of the cylinder perpendicular to the a-axis, which is kind of what we would want, right? Because that's the long axis. You could change it another way. For example, you could put it along C, and then they would look like weird disc sort of things. It would look kind of, so that's a fun thing to mess around with. Like you can make some pretty funky looking shapes by changing all these different ratios of size to the kind of shape that we use. But we're going to make something that's a little bit well behaved. Okay, now I mentioned it this morning that we need, there's basically a filter that puts each phase into the, or sorry, puts each phase type into the box. So there's a filter that puts primary phases in. We use that, it's called pack primary phases. There's a filter that puts matrix phases in. It's not called pack matrix phase because the matrix phase, there's nothing to pack. It's called established matrix phase. So everything should just default nicely here. And just like pack primary phases, you can use a mask for the matrix phase. So if you, again, only want to put the phase on certain voxels and you happen to have a mask that says where you want to put it, that's an option. Again, though, there's no real computation that's done in this filter. It's basically just putting the same number everywhere. So it's pretty straightforward. You can have multiple matrix phases, by the way. It just gets a little weird without Dream3D fill space then, because they're each like competing to fill space. So that's a question that sometimes comes up. You try it yourself and see what happens. So now we need to put our fibers in, and unfortunately for each of these 3 different filters, we've chosen different words to describe them. So we had pack primary phases, established matrix phase, and now it's insert precipitate phase. So we call it that because again, we're not packing to fill space. We're actually putting the precipitates, or fibers in this case, into the volume one at a time. Turns out that we found that to be kind of the best way to try to optimize both all the features of the phases that we care about, their sizes, their distributions, and the radial distribution function. Let's just do it one at a time. So it's a little bit slower than pack primary phases usually. It does need an array that we haven't computed called boundary cells. You'll see that that's red. That's because if you remember back when we create a precipitate phase, we have an option to set a fraction of the precipitate phase to lie along a primary phase boundary. Now we don't have a primary phase here, so it doesn't matter. But the filter isn't smart enough to know, so it still asks for boundary cells. So we need to compute it for the filter. And so just like we've done a number of times when you put a filter in and everything's green except for one thing, what I usually do is you just search for the thing it wants. So we'll search boundary. And there should be a filter called find boundary cells image. Because it's an image geometry because it's voxels. Now we need to select the feature IDs. So those are right here in the synthetic volume data container. One thing I'll note about this filter is that it has the option to ignore feature 0. So if you remember, we talked a little bit yesterday about the fact that feature 0 is kind of the garbage bin feature. Let's say, for example, you had a bunch of speckle noise in the EBSD scan and you stuck that speckle noise into feature 0. If you uncheck this option and ran this filter, it's going to identify every pixel around that speckle noise as a boundary pixel, which seems kind of weird. So maybe you want to ignore it. You might also, for some reason, want to treat the boundary of your box as a boundary. The surface of the box is a boundary, and so you have that option to select include volume boundary, and then I think simply what's going to happen is all the pixels that touch the surface are going to be called boundary cells. But we can just leave it as default. We don't need any of that. Now this should all be happy. And again, we have very similar options to pack primary phases. You can make it periodic if we wanted to. I'm not going to. We could match, if we had set a radial distribution function, you need to manually say, try to match it in this filter. That adds a lot of additional computation time, by the way. That's why we're not going to mess around with it right now. And of course, use mask. Same thing as the primary phase. If we have a mask and we only want the fibers to go in a certain part, we can set it. It does the same thing. If you happen to have a list somewhere else for your precipitates that you got from some other code, you could just give it to Dream3D and let it fill space. And again, this shape description array thing is just like for the primary phase. It's going to write out a file that says this is what Dream3D was trying to match to. But remember, that's for idealized shapes, not the things that actually fill space that we actually put into the box. Okay, that's it. So we don't need to do any crystallography for this example. So we're going to do write Dream3D data file. Put it into my output folder where I've been putting everything for the past 2 days, and I'll call this fibers. And I'm going to start it. So it shouldn't be too long. I forget, yeah, that's about right. It's about 30. So it's pretty quick. I set values here. If you recall, I made the box pretty small, 30 microns on edge, and I set fibers that were relatively big, almost 8 in their spherical and diameters. So just mostly to not get a ton of fibers, because I'm going to do a visualization thing in ParaView where we can look at the fibers. So mine ran pretty quick. It's already done. I'm going to go ahead and open that in ParaView. So we get our box, just like we did for the other case. I'm going to change to surface, and then we'll change to feature IDs. And I've got some fibers, fiberish looking things. We didn't spend a lot of time making this look really nice. This was mostly meant to just motivate how this works. I think the critical thing to note here is if you look at the little axis jack down in the corner, well, I've oriented it now so that X is going up and down like this, and all my long axes are long X, which is what we wanted, if you remember correctly. We did 10 to 2 to 1. If I kind of orient this way, you can see that they are, along the Y-axis, which is the B aligned with the B-axis. They're squashed a little bit, and of course along X or Z, which is this guy like this. They're about half. It's not exact. Remember the distributions that we looked at that got set automatically by doing the rolled preset values. There was some spread to them. If we wanted this to be really tight, we could have messed with those parameters manually, but we didn't. So some fibers, nothing fancy, obviously. So there's actually been a lot of work on making much fancier looking fiber sort of images at the base in particular. But I think this is fine for the workshop. I'll do one other thing, which is you don't have to do this, but just to show you the fibers. Feature 1 is the matrix phase. So I'm going to threshold on feature 2 and above. Depending on how fast your computer is, this might be quicker, but just to show you the fibers inside are these nice little cylinders. And remember, we put it so that they had their caps, so along the long axis. So some of the fibers, stop, some go all the way. Remember, there's a distribution of size. It wasn't a big distribution, but there was a little bit. And this is an example where if I changed it to periodic boundary conditions, we'd probably see this fiber continue on the other side. It got cut off by the boundary of the box a little bit. So you go, there's some fibers. Any questions about precipitate phases and matrix phases? Tony?
So there was a question in the chat that was basically asking about how to control the shape of the precipitate phases independently of the matrix grains. I was suggesting omega-3, but perhaps there are other things you can do.
Sure, yeah. So if I go back in the stats generator, and I have, let me make this, there we go, let's make this a bit bigger. So I've got my precipitate phase selected here, or my fibers selected. And the two things that Dream3D thinks about with shape are aspect ratios and omega-3s. So aspect ratios in this case I've kind of already set. Remember, omega-3 is independent of aspect ratio. So maybe I want to make objects that are 10 to 2 to 1, but are cuboctahedral, or let's say just have facets to them. So if I go to omega-3 here and I click on it, you'll notice that it peaks way close to 1. So everything's going to be spherical-ish. So I'm going to change this so that I shift the peak a little bit down, closer to like 0.7-ish. Okay, crank it up even more. There we go. Yeah, 5. You don't have to do this. This is just me kind of showing. So I've pulled the peak down a little bit, closer to 0.7. And then the key thing to note, though, as I mentioned this in the first session, is that omega-3, which is going to let you get more fine-grained control over the shape, only can impact superellipsoid shape types. So if I go into established shape types, I had cylinders here. So I basically told Dream3D, make these things cylinders, not even ellipsoids, right? So I'm going to change this to, I have no idea what this is going to make, by the way. I'm going to change this to superellipsoid and then run it. We'll see what happens. It should make some really weird looking things. Yeah, you can see it's also taking a bit longer because it's making really weird looking things.
With these precipitates, does it make sure that they don't overlap each other, or can they kind of run into each other?
Great question. They can run into each other. We used to have some capability to make them totally hard, so that they would not. So when they impinge, like if they were to overlap, they would kind of repulse each other and have like a space between them. There were some issues with that, so we went back to the other way where they can overlap. There are ways if you want to have if you want to add that repulsion in theory, that should be added in the RDF. Because that affects the probability that the feature that's going to be next to you, will, there's a function of, to exclude, spread them out.
Yep.
So that'd be the proper way to do it. So we didn't do that. So you could actually see in the, I think, directly going through.
But I assume the RDF is just on like the centroids of the shapes, right? So like if you have some really funky shape, they could definitely still.
They still could, yeah. So it becomes a bit of it's a big multi-parameter optimization problem. Sure. And so the way that, there's definitely better ways to do this now than when I think a lot of this fundamental code got written, but it's basically at this point just working with it yourself to kind of figure it out. Or if you have grad students, you can do grad student descent and let them figure it out. You guys haven't heard that one? That's like the machine learning terminology for it. So when you go read machine learning articles on brand new architectures for neural networks and you wonder how they came up with it, it didn't come out of the blue. It was probably because they have 10 grad students who worked a lot to figure out what the architecture and hyperparameters should be. Let's see what this looks like. I'm kind of scared.
Oh, it'll be fine. What could go wrong?
Oh yeah, yeah. So it made really weird, faceted looking sort of shape. Remember? Yeah.
Yeah.
That does kind of look like that. Yeah. Remember, these were. I set the distribution around 0.7-ish, which, if you recall from the example I showed, is kind of like a cuboctahedron or close to it. And so these kind of do look like cuboctahedrons now, and of course, but remember, it's independent of aspect ratio, so they're stretched out. So that's kind of cool looking. So yeah, you can start imagining you can make really complicated looking things if you wanted to. All right. Any more questions about that? Yeah, how are you talking to around the? So that's in stats generator, you have to make sure that you have two phases. You have to have both the matrix phase and the fiber phase. And then in the pipeline, you have to make sure you put the matrix phase in. So this is established matrix phase built in. I'll go ahead and not close this one. I'll just open up a new window. So if you can, well, I want to make one more structure, and then it's, I think Greg's going to talk about GBCD stuff. So should have time to do this one more. This is one that a lot of people have asked about before and thought that we couldn't do. It turns out you can do it. You just have to think outside the box a little bit on what needs to be a primary phase. So we're going to make a bimodal grain size distribution. And historically, a lot of the times when people try to do that in Dream3D, they try to force it into the single primary phase, but you're never going to be able to do that because it's a log normal distribution. What makes more sense is to make two primary phases that have fundamentally very different grain size distributions. So we're going to do that right now and try to make something that's kind of like having some abnormal grains in the structure. So I'm back in Dream3D. I need to get stats generator because I opened up the window. Whoops. So we're going to have a primary phase. Like I said, we're going to try to make a primary phase that's just kind of normal grains, and then we're going to make a second primary phase that has really big grains. Let's see here. So I set, I think I just used default values for the first primary phase. Yeah, 1, 1. Yeah, okay. So this is just default, nothing, you can just leave it like it is. We do have to click create data because we always have to do that to kind of initialize everything. It's going to calculate all of our stuff. And now we're going to add in our second primary phase. So you can have multiple primary phases. I'm not going to do any crystallography for this example. I just want to show the features. Fraction, I'm going to set this 80% of the small grains and 20% of the big grains. So this is going to be my big phase, so I'll set it at 0.2. You see it dynamically updates because I didn't set the fraction of the previous phase, so we'll go change that in a second. It's going to be primary, and I'm going to call this abnormal grain growth, maybe. AGG, you can name it whatever you want. And then if I go back, I'm going to go back to my first primary phase and change its volume fraction to 0.8. So I have exactly 80% of the small grains and exactly, obviously it's random, but about 20% of abnormal grains. So I'm on the primary tab, click the cogwheel. I'm going to change this to 0.8, and now it updates to exactly 0.8. Okay, so in my abnormal grain growth, or my abnormal phase, I'm going to set the mu to, I'm going to triple the size. I'll set it to 3. But of course, remember, this is a log distribution, so I triple mu, and it significantly more than triples the actual value. And then I set this, I kept the sigma at 0.1. The bit step size doesn't matter because we're not going to mess with the with any of the shape distributions or anything. So I'll just leave it like it is. You can see we've got a ton of bins, but it doesn't really matter because we're not going to vary anything with the shape. We're going to keep them equiax. And then I set the min and the max cutoff to 5. So basically all I changed here was the mu to 3. In the second primary phase, I'll put create data so that it generates everything for the second phase. So now what it should look like is that we have two phases, two primary phases. I've named the second one AGG, and I'm just using, for abnormal grain growth, I'm just using default values here, except for I changed the second primary phase, the 20% phase, to have a mu of 3 instead of 1. Now we need to do all the same things we did before. We need to make a box, we need to make the shape types, and then we need to put them in the box. So again, you'll probably start seeing that we do a lot of the same steps for synthetic building. We have to make the synthetic volume, initialize synthetic volume. And I'm going to go check to see the exact values I used. I guess I forgot to write this one down. I kept them as default. I should have realized that I did that on purpose. So I kept these on default. And what that means is that so remember, the box is about 32 microns, quote unquote, and my average feature size for my second phase was like 20. So what should happen is I should have maybe like 1 giant abnormal grain, maybe 2. I think when I did this last week, I had 2. I guess we'll see. I need to make the shape types. So just like we've done before, establish shape types. I'm going to leave these as ellipsoids, nothing fancy here. And now I need to put the primary phases in. So if you remember, the filter to do that is pack primary phases. Now, a question you might have is, do you have to run this filter twice? Because we have 2 primary phases. That might be a natural question you have. The answer is no. This filter is going to pack for however many primary phases you've set in stats generator is going to pack all of them at once. So you only have to run this filter 1 time. If you run it twice, weird things will happen. So just do it once. We'll do everything default here, nothing that we need to change. And then we'll write out the Dream3D file. I'm a little here, but really small like that. I guess. So I set the file type. I'll go ahead and start it. So in this case, it's going to take a little bit longer because it's got some giant frame put in the box. Probably is what happened. You see, we try to get some feedback on how much longer we can take. Not a particularly large structure. Nowadays, back in the day, it was pretty big. Opening that file in ParaView, like we've done before. I only have 2 arrays. I just have the feature IDs and the phases. So phases will matter now because I've got 2 primary phases. It's not just going to be 1 everywhere. Change this to surface. So I guess let's look at that first. Yeah, okay. So I ended up with 2 giant grains. Or 2 somewhat big grains, because I changed it to phases. I changed this to feature IDs. So there's a couple things to note about this that are interesting to note. One is that when you start trying to do something like this, it's going to, with really big things fitting into the box, the best place it's going to almost always find to put that's going to be in a corner or on a surface. So a couple things to recommend there. Either make your box huge if you want to make sure you get a full grain volume from something that's big, or put on periodic boundary conditions. Another thing to note is that if you're really close, if you look really closely, the boundary of this grain looks a little funky. And that's just a feature of how we build space. You know, if you recall, I said it's kind of like a pop model, but it's not really. It doesn't have any interfacial energy component to it. So there are some, let me threshold out just a like the other grains are kind of fitting into it. And that's because of this weird space filling thing we've done. So this is not ideal. This is clearly not like how a real abnormal grain would look. So I would never recommend using this to try to create like an actual bimodal structure. But what people have done and what you can do is use this to maybe as a starting point and then put it into Spark. So put it into something that's actually going to do an evolution. And the nice thing about this is it lets you control exactly what the initial states of this is, which could be hard to do a priori from a physics space kind of thing. We could do this more directly, but it has this downside of these are clearly not realistic energy, like the boundaries here are not realistic from an energy perspective. But just kind of drive the point that you can do some interesting things with multiple phases. You can imagine having multiple primary phases and multiple precipitate phases. You can make a pretty complicated structure. I guess last thing I'll mention is a question we get asked a lot about is, can I make structures that have twins or labs? And the answer is kind of. There's a filter that's called insert transformation phases that really can only do sigma 3 twins. It's also got a little bit of a bug in it that's getting fixed. And that does work pretty well if you just want to make like a twins kind of nickel type structure. That actually works quite nicely. Making other types of transformed phases, like titanium structures with laths or steel structures that have particular orientation relationships. In theory, that was what the point of that insert transformations filter was going to do for a whole variety of orientation relationships. We never got to fleshing them all out, so can't quite do it yet. People have though used Dream3D to kind of work around that in some clever ways. And if you're interested in that, trying to make like really complicated basket weave type structures with Dream3D, there's been some published papers on that. I'd be happy to point you to those references to kind of see tricks you can play to try to get around it. But I would certainly never claim that it makes super realistic looking complicated basket weave structures. Those are pretty hard. Okay, well, I think we have 5 minutes before Greg's going to talk. So I figured I'd stop there. And if there are any questions anybody has about synthetic building or anything else, happy to answer them now. Philosophical questions about synthetic building or anything like that.
Can you elaborate on that last point? Like if Dream3D isn't the correct engine for making basket weave or lattice type transformation structures, where would you go?
I'd probably do an experiment and collect the data experimentally. The structures are quite complicated, right? And so if you have, if you have a complicated steel structure or a titanium structure with a lot of labs, assuming you can get good EDSD patterns, that's a whole thing in its own right, but assuming you can get good quality patterns and actually index it, that's going to be your best way to get a good structure. Making them synthetically is quite difficult. It's not that we don't have, I would say, first order, like in Dream3D, you can create geometrically what kind of looks like lab structures. The problem is the complexity of how to make the original parent phase is hard. So it's hard because in general, we don't know what the parent phases look like unless we use a code to reconstruct the parent phases from data that we have collected experimentally, and then we kind of get a sense of like, oh, this is generally what the parent phases look like. And the reason that's important is because that's what Dream3D wants to start from to then put these transformed twins or labs into the structure. And so right now we just make nice equiax structures as the original parent phases, then we put these twins in, and it never quite looks like so the structure that we looked at yesterday in the Midas data set, you get these massive grains that are heavily twinned in a whole variety of complicated ways. And we just have never figured out a way to recreate that with this kind of sort of shape type insertion. So I guess the long-winded answer to your question is I don't know of a good tool that creates really realistic looking synthetic structures that are heavily twinned or have a lot of labs. There has been a lot of work on quantifying the distributions of twins and highly twinned materials. I point you to the work of a guy named Will Lempey, who did a lot of really nice work in his thesis on developing that all out. But that next step of, okay, now we've got this great description and great data set, I want to make a synthetic builder from that. I think that's still a research gap and we don't quite have. We have done some work at AFRL, this is not in Dream3D or released, but using machine learning techniques, using both variational autoencoders and generative adversarial networks to make really complicated looking structures that fool world experts in titanium. I won't claim they're ready for prime time, but that's another totally different alternative, and that's not released yet. Hopefully there'll be a paper on that. We'll get around to that. But that still requires that we need experimental data to train on. So,
What about structures with like heterogeneous orientation?
Sure, yeah.
So a portion that's say recrystallized in random, a portion that maybe has some imposed texture.
Sure, yeah. So the way you would do that is if you knew generally the space where that texture varies. Select, you can only insert that phase into a certain subvolume using the mask. Mm-hmm. And so you create the primary phase that, let's say, is highly textured, very high. Maybe it's titanium and it's like a region that has an extreme C-axis alignment, makes a microtexture region, as it's called. You would have that region be highly textured, and then you would have the surrounding medium primary phase, which you would insert in the inverse of the mask, be random texture. But people have done that. We've done that actually for the exact problem I just described, trying to create microtexture regions. Titanium structures. Okay. So I think we're right at 12:15 now, so I'll stop. Obviously, this afternoon there'll be a lot more time to